Hello friends, welcome to CS Tunes. Today we are going to discuss about context-free grammars. Before going into details of context-free grammars, let us discuss what is a grammar. A grammar is a set of rules to define valid sentence in any language. If we talk about theory of computation, then grammars can be represented mathematically using four tuples. So these are the four tuples that are required to represent a grammar. The first tuple is Vn. Vn means a finite set of non-terminals. Non-terminals are variables and can be represented using capital letters. The second tuple is Vt. Vt is a finite set of terminals. Terminals are constants and can be represented using small letters. Then S. The next tuple is your S. S is a start symbol and it belongs to the set of non-terminals. That means the value of S is a variable. Then P is the production rules. Production rules are the rules which are used to represent any grammar. Now let's talk about context-free grammars. So if we are talking about context-free grammars, it is represented using the production rules of the form alpha tends to beta. Alpha over here belongs to the set of non-terminals. That means in place of alpha, we can have a single non-terminal. And beta here belongs to a set of terminals union the set of non-terminals. That means beta is a combination of terminals as well as non-terminals. So beta is a string which is formed using terminals and non-terminals. Also beta can be replaced by a null. So we can have a null in the right hand side because of this asterisk, that is our star closer. So according to this production rule, we can find out that on the left hand side there is a single non-terminal. That means on the left hand side there is a single variable, and on the right hand side there is a combination of terminals and non-terminals. That means a combination of constants and variables, or it can be replaced by a null. That is your asterisk. Now there are 2 points which you must know. The first point is that every regular grammar is context free, and hence the regular language corresponding to this regular grammar is also context free. So it is always possible for us to design a context free grammar for any regular language. Now let's see an example. According to this example, we need to find a language corresponding to a context-free grammar that is given over here. So the grammar which is given to us has two production rules. The first production rule says that S tends to A, S, B, and the second production rule tells us that S tends to AB. So if we talk about the first production rule, in this A is a non-terminal, A is a terminal and B is also a terminal and S is a non-terminal. That means the value of S can be replaced by any terminal. Similarly, if we are talking about the second production rule, in the second production rule, on the right hand side, there is a combination of two terminals. That means two constants. So they cannot be replaced by any other value. Now we want to see which language is generated using this production rule. So let's start with our first production rule, S tends to ASB. So we are taking S tends to ASB. On putting the value of S as ASB again, we are putting the value of S in this rule as ASB. So we will have S tends to A copied as it is. Then the value of S is replaced by ASB, and then this B is copied as it is. So in this way, you can see how we are replacing the value of S in this particular rule. On the right hand side, we are replacing the value of S by ASB. Similarly, if we are going to replace the value of S by ASB n minus 1 times. So we are going to replace the value n minus 1 times in this particular rule. So we will find that our rule becomes s tends to a to the power n minus 1, s b to the power n minus 1. Now s over here is a variable again, but a and b are becoming constants. Now if we put the second production rule, that is s tends to ab, in place of this particular s, then the rule becomes s tends to a to the power n minus 1 a, b to the power n minus 1. In general form, we can write it as a to the power n, because n minus 1 plus this a gives us a to the power n. Similarly, b to the power n minus 1 will give us b to the power n. So we can say that the language generated for this particular grammar is a to the power n, b to the power n, where n is greater than equal to 1. Why we are taking n is greater than equal to 1? Because a and b cannot be replaced by null. These are constant and the minimum string which is possible is ab. So that means at least one a and at least one b will be there in our language. That's why n is greater than equal to 1. Suppose there is one more production rule given as s tends to epsilon. In that case, we can have the value of n as n is greater than equal to 0, because in that particular case, the grammar can also accept a null string. So in this example, we have seen how we can generate a language for a particular context-free grammar. Now in the second example, we are going to see that how we can generate a context-free grammar for a language given to us. So in this, the language given to us is WC, W to the power R, where W belongs to the set of A, B asterisk. If we talk about WC, W to the power R, so this R means reverse. That means a complement of this W. So on the right hand side of C, we are having the complement of the same string which is present on the left hand side of C. W can take the values as A, or it can take a value as B, or it can take a value as asterisk or epsilon due to this asterisk, that is our star closer. So it can have three values. It can have epsilon, it can have A, it can have B. And also it can accept any combination of A, B. Now let's see what are the different strings that can be accepted by this particular language. So the minimum string which can be accepted is C. If we are replacing W by null, that means epsilon, then the reversal of W, that is null, will always be null. So we will have a string as a single C. Now the second string that can be accepted is if we are taking W as A, that means A on the left hand side, so on the right hand side also there will be A. So the minimum string is ACA. Now the third minimum string which is possible is if we are taking B on the left hand side and the reverse of B will be B, that means on the right hand side there will be B. So the third minimum string possible is BCB. Now rest of the strings can be in the combination of A and B. So if we are taking AB on the left hand side, then we will have BA on the right hand side of C. Similarly, if we have BA on the left hand side, so we will have AB on the right hand side of C. Similarly, we have ABA on the left hand side, so ABA on the right hand side of C. Now, if we talk about this, the minimum string that is possible is C. So, the grammar will have a production rule as S tends to C. That means the variable S can be replaced by a single C to accept the minimum string. Now, according to next minimum string ACA, we have the production rule as S tends to ASA. ASA means your S can be replaced by C. So the minimum string ACA is accepted over here, ACA. Now the third minimum string is if it is starting with B and it is ending with B. So we have S tends to starting with B and ending with B, and in the middle we can have a variable as S that can be either replaced by C or it can be replaced by ASA. So these are the three production rules that forms a grammar for this language. Now let's check whether the grammar produced by us is correct or not. So let us take any example. Let's say we are checking for this particular string. So BACAB. We are going to check whether this string is accepted by our grammar or not. Now let's start. So the first production rule we are going to take is S tends to BSB. So the first production rule is BSB. On replacing the value of S by S tends to ASA, that is our first production rule. So we are replacing this value of S by ASA. So we will have S tends to BAS A, B. Now, in the middle, we want to have a C. So, we will take another production rule, that is our S tends to C, that is our third production rule. So, on replacing S by C, we will have B, A, C, A, B. That is our required string. That means the string is accepted and hence proved the grammar which is produced by us is correct for the language given in the question. Similarly, following the same steps as I have told you in this particular video, you can find any language corresponding to a context-free grammar or any context-free grammar corresponding to a given language. You can solve any of the questions which is provided to you in the similar manner. Thanks for watching our video. For further queries, comment in the comment section. Stay tuned for more videos and do like and subscribe our channel CS Tube. Thank you.